Close your eyes for a moment and imagine drifting through the quiet darkness of space. A place where nothing seems to move, yet everything is constantly being shaped by forces you can't see. Tonight, we're not just admiring the stars from a distance. We're uncovering the hidden powers that actually run the universe. Because here's the surprising truth. Most of what controls the cosmos isn't visible at all. The brightest objects, the stars, the galaxies, the glowing clouds of gas, are only the decoration. The real architects of reality are invisible forces working slowly, patiently, and endlessly in the background. These quiet giants, gravity, dark matter, dark energy, and the subtle fields that thread through space decide how galaxies spin, how stars are born, how space itself stretches, and even what the far future of the universe will look like. Yet they rarely get shown in diagrams, and when they do, they're reduced to simple arrows or labels that barely hint at their true influence. Tonight, we're going to explore them as they really are. Unseen, enormous, and fundamental to everything we know. As we move through this journey, let your thoughts loosen and drift with the rhythm of cosmic time. The universe operates slowly, with changes measured not in minutes or years, but in epochs and eons. Understanding it doesn't require effort, only curiosity and a willingness to let the invisible world reveal itself, piece by gentle piece. So settle into the stillness between galaxies, and let's begin our peaceful exploration of the quiet forces that shape the universe from the shadows. The invisible architecture. In every moment of your existence, you are held gently in the embrace of forces you cannot see. Forces that have operated since the beginning of time, and that will continue long after the last star has faded into darkness. The universe is built not primarily from the things we can observe directly, but from invisible forces and unseen substances that make up most of reality. And understanding this invisible architecture requires us to shift our perspective away from the bright and obvious toward the subtle and the hidden. When we look at the night sky with our eyes alone, we see perhaps a few thousand stars scattered across the darkness. But this visible light represents only a tiny fraction of what exists out there in the cosmic ocean. For every particle of matter we can see, there are dozens more that remain invisible. And for every force we can feel directly through our human senses, there are others operating on scales so vast or so small that our bodies evolved no way to detect them without instruments and mathematics to extend our perception beyond its natural limits. The quiet giants we will explore together are not quiet because they are weak, but because they work in frequencies and dimensions that our senses were never designed to hear or see. And they are giants not because of physical size, but because their influence extends across distances that make the space between planets seem insignificant. These forces shaped the first moments after the Big Bang, when the universe was unimaginably hot and dense. They guided the formation of the first atoms and the first stars. They gathered matter into galaxies and clusters and the vast cosmic web that stretches across billions of light years, and they continue their patient work in this present moment, pulling on every atom in your body with the same invisible hands that sculpt the orbits of planets and bend the paths of light itself. To understand these forces is to glimpse the hidden mechanisms that make existence possible. The subtle rules written into the fabric of space-time that allow complexity and structure and life itself to emerge from what began as a nearly uniform sea of energy. As we drift through this exploration, we will discover that emptiness is not truly empty, that darkness contains more substance than light, that the space between stars is alive with invisible currents and fields and particles, and that what seems solid and permanent is actually a temporary arrangement of forces in delicate balance, a pattern that persists for a while before dissolving back into the cosmic dance. Gravity's patient architecture. Of all the invisible forces that shape the cosmos, gravity is perhaps the most familiar, yet also the most mysterious. A force so gentle that you barely notice it in your daily life, yet so powerful that it holds entire galaxies together and determines the ultimate fate of the universe. Gravity is the quiet giant that never sleeps and never tires, pulling constantly on every piece of matter in existence with a patience that spans billions of years, working slowly but inevitably to gather cosmic material into structures and to guide those structures through their long evolutionary journeys. Unlike the other fundamental forces that can push or pull, depending on circumstances, gravity only attracts, only draws things together, creating a cosmic architecture built entirely from the gentle accumulation of countless tiny tugs that individually are almost negligible, but that collectively shape reality on the grandest scales imaginable. Every atom in your body is pulling gravitationally on every other atom in the universe, and every other atom is pulling back, creating a web of invisible connections that links you to the most distant galaxy and to the earliest moments of cosmic history. The strength of these gravitational pulls decreases with distance following a simple mathematical rule, becoming weaker as objects move farther apart, but never quite reaching zero, no matter how far the separation, which means that in principle, everything in the universe is connected through gravity to everything else. Though in practice, the pulls become so faint at cosmic distances that they have no measurable effect. Gravity shapes the universe through a slow process of gathering and organizing matter that operates across time frames difficult for human minds to comprehend, beginning with tiny variations in density that existed in the very early universe, when matter was spread almost uniformly through space, but not quite perfectly so. These tiny density differences, fluctuations of just 1 part in 100,000, were enough to create slightly stronger gravitational pulls in the denser regions. And those stronger pulls attracted more matter from the surrounding areas, which made those regions even denser, which increased the gravitational attraction even more, creating a feedback loop that over hundreds of millions of years transformed nearly smooth distributions of matter into the intricate cosmic web of galaxies and clusters and superclusters we observe today. The fabric beneath reality. Einstein taught us that gravity is not really a force pulling objects together through empty space, but rather a consequence of the way mass bends and curves the fabric of space-time itself, transforming our understanding of the invisible architecture from one of forces acting through emptiness to one of geometry itself becoming dynamic and responsive to the presence of matter and energy. This insight, which forms the foundation of general relativity, reveals that what we call space-time is not a passive stage on which cosmic events unfold, but an active participant in those events, a flexible fabric that can be stretched and compressed and twisted by the presence of massive objects, creating valleys and hills in a four-dimensional landscape through which everything must travel. Imagine space-time as resembling an infinite rubber sheet stretched flat across eternity, perfectly smooth and featureless in the absence of matter. But when you place a massive object like a star or planet on this sheet, it creates a depression, a gentle valley in the fabric itself. And anything moving near this valley will naturally roll toward it, not because of some mysterious force reaching out through space, but simply because the geometry of the space itself has been altered by the presence of the mass. The greater the mass, the deeper the depression it creates in space-time, and the more influence it has on the paths of objects moving nearby, which is why planets orbit stars and moons, orbit planets, and why light itself bends when passing near massive objects. following the curved geometry of space-time, like a car following the curves of a hilly road. This geometric understanding of gravity helps us appreciate how deeply the invisible force is woven into the structure of reality itself. Not something added on top of space and time, but an inherent property of the four-dimensional continuum in which we exist. Space-time responds to the presence of mass and energy by curving, and objects respond to that curvature by following what physicists call geodesics, the straightest possible paths through curved space, which from our perspective appear as orbits and trajectories shaped by gravitational attraction. The mathematics of general relativity describes precisely how matter curves space-time, and how that curvature affects the motion of other matter, creating a complete and elegant description of gravity as geometry. Though the equations are complex and require careful study to fully appreciate their depth and beauty. Gravitational waves in the cosmic ocean. Just as a stone dropped into still water creates ripples that spread outward from the point of impact, massive objects accelerating through space create ripples in the fabric of space-time itself. Disturbances that propagate outward at the speed of light, carrying information about the violent events that created them. These gravitational waves were predicted by Einstein more than a century ago as a consequence of his geometric theory of gravity. But they are so incredibly faint that detecting them required building the most sensitive measuring instruments ever constructed. Devices capable of detecting changes in distance smaller than the width of an atomic nucleus across measuring arms several miles long. Gravitational waves represent perhaps the ultimate manifestation of gravity as a quiet giant, invisible and nearly undetectable, yet carrying enormous amounts of energy through the cosmos, generated by some of the most dramatic events in the universe, including the collisions of black holes and neutron stars, the explosions of massive stars as supernovae, and even the faint whispers remaining from the Big Bang itself. When two black holes spiral together in their final dance before merging, they create gravitational waves that shake space-time like ripples on a pond. And though these waves have traveled across millions or billions of light years by the time they reach Earth, becoming incredibly faint in the process, they still carry within their oscillating patterns detailed information about the masses and spins of the black holes that created them, and about the fundamental nature of gravity itself. The detection of gravitational waves beginning in 2015 opened a completely new way of observing the universe, allowing astronomers to sense cosmic events through the geometry of space-time rather than through light or other electromagnetic radiation, providing information about phenomena that are completely dark and invisible to traditional telescopes. As gravitational waves pass through space, they stretch and compress the fabric of space-time in alternating directions, making distances oscillate by infinitesimal amounts that sophisticated detectors can measure by bouncing laser beams back and forth along long perpendicular arms and watching for tiny differences in the time it takes the light to complete its journey. The waves themselves move through everything without being blocked or absorbed, passing through planets and stars and galaxies as if they were not there, carrying their information pristinely across cosmic distances without being scattered or distorted the way light is affected by its interactions with matter. Dark matter's silent embrace, surrounding every galaxy like an invisible halo, extending far beyond the visible stars and gas into the dark reaches of intergalactic space. There exists something that we cannot see, but whose gravitational effects are unmistakable and profound. Something that astronomers call dark matter, even though we do not know what it is made of or how it behaves, except through its gravitational influence on visible matter and light. Dark matter is perhaps the most mysterious of the quiet giants, making up about 85% of all matter in the universe, yet remaining completely invisible to our telescopes, because it does not emit, absorb, or reflect electromagnetic radiation of any kind, existing in a shadowy realm parallel to the ordinary matter from which stars and planets and living things are made. We know dark matter exists because galaxies rotate too fast, their outer regions moving at speeds that should fling them apart into space unless they contain far more mass than we can see in their stars and gas. And because clusters of galaxies hold together despite the visible matter being insufficient to provide the gravity needed to bind them. We know dark matter exists because light from distant galaxies is bent and distorted as it passes through regions of space that appear empty, but that must contain enormous amounts of invisible mass to create the gravitational lensing effects we observe. We know dark matter exists because computer simulations of cosmic structure formation cannot reproduce the universe we observe unless we include large amounts of this invisible substance whose gravity helps gather ordinary matter into the galaxies and clusters we see. Yet despite decades of intensive searching, we have not directly detected a single particle of dark matter, and we do not know whether it consists of exotic particles that interact only through gravity and possibly through weak nuclear forces, or whether it represents something even stranger, like modifications to gravity itself at large scales. Though most evidence points toward dark matter being some form of particle that simply does not interact electromagnetically. The distribution of dark matter throughout the universe follows patterns revealed through gravitational lensing and through the motions of galaxies, showing that dark matter forms a cosmic scaffolding or skeleton upon which visible matter accumulates. With dark matter halos surrounding galaxies and dark matter filaments connecting clusters in the vast cosmic web, the invisible scaffold of galaxies. The dark matter halos that surround galaxies are not uniform spheres, but complex three-dimensional structures with their own intricate architecture shaped by billions of years of gravitational interactions and cosmic evolution. And understanding this invisible scaffold helps us appreciate how ordinary matter was able to organize itself into the beautiful spiral and elliptical galaxies we observe scattered through space. In the early universe, shortly after the Big Bang, dark matter began clumping together under its own gravity, faster than ordinary matter could, because dark matter felt only gravitational forces and was not slowed by electromagnetic interactions or by pressure from radiation. These early clumps of dark matter created gravitational wells, valleys in the space-time fabric into which ordinary matter could fall, once the universe had cooled enough and expanded enough for gravity to overcome the outward pressure of radiation. The ordinary matter falling into these dark matter halos heated up as it compressed, eventually becoming dense and hot enough in the centers to ignite nuclear fusion and form the first stars, which gathered into the first galaxies within the gravitational embrace of the dark matter structures. Without dark matter to provide the gravitational framework and to hold everything together with its invisible hands, galaxies as we know them could not exist, because ordinary matter alone does not have enough gravity to gather into and maintain the large rotating structures we observe. The dark matter halos extend far beyond the visible edges of galaxies, continuing outward for hundreds of thousands of light years into what appears to be empty space, gradually fading away as the density of dark matter particles decreases with distance from the galactic center. These extended halos affect the motions of satellite galaxies and globular clusters orbiting in the outskirts of larger galaxies, and they interact gravitationally when galaxies approach each other, creating complex tidal forces and distortions that can trigger bursts of star formation and that eventually lead to galactic mergers when two dark matter halos merge into one. The properties of dark matter halos, including their total mass, their shape, and their internal structure, play crucial roles in determining the characteristics of the galaxies they host, creating relationships between dark matter properties and galaxy properties that astronomers study to learn more about this invisible substance. dark energy and the accelerating cosmos. If dark matter is mysterious, then dark energy is even more puzzling and more difficult to comprehend, representing not a substance or particle, but apparently a property of space itself. An energy density associated with the vacuum that creates a kind of anti-gravity effect, pushing space apart and causing the expansion of the universe to accelerate rather than slow down, as gravity alone would demand. Dark energy makes up about 68% of the total energy content of the universe, dominating over both dark matter and ordinary matter. Yet we have no clear idea what it is or why it exists, only observations showing that something is pushing the universe apart with ever-increasing force. The discovery of dark energy came as a complete surprise to astronomers in the late 1990s when observations of distant exploding stars called supernova revealed that the expansion of the universe is speeding up rather than slowing. As had been expected, a finding so unexpected that it was initially doubted and required confirmation through multiple independent lines of evidence before the astronomical community accepted it. The realization that the universe's expansion is accelerating implies that some form of energy with repulsive gravitational effects must permeate all of space. And the simplest explanation involves what Einstein called the cosmological constant, a term he introduced into his equations of general relativity to represent a constant energy density of empty space itself. If every cubic meter of space contains a certain tiny amount of energy simply by virtue of being space, and if space itself is constantly expanding and creating more cubic meters, then the total amount of this vacuum energy increases over time, and its repulsive gravitational effect grows stronger, eventually coming to dominate over the attractive gravity of matter and causing expansion to accelerate. This concept challenges our intuitions about emptiness and nothingness, suggesting that even the purest vacuum is not truly empty, but seethes with energy at the quantum level, energy that manifests on cosmic scales as the dark energy pushing galaxies apart. The nature of dark energy remains one of the deepest mysteries in physics, with theoretical calculations predicting values for vacuum energy that differ from observations by enormous factors, creating what physicists call the cosmological constant problem, one of the most significant unsolved puzzles in fundamental physics. The geometry of invisible energy, dark energy, affects the universe not through any local interaction or force that we can point to in a specific place, but through its influence on the global geometry and dynamics of spacetime itself, determining how fast space expands and how the expansion rate changes over time, shaping the ultimate fate of everything that exists. In a universe dominated by matter alone, the mutual gravitational attraction of all the galaxies and dark matter would gradually slow the cosmic expansion, perhaps eventually stopping it entirely and causing the universe to collapse back on itself in a big crunch, or allowing expansion to continue forever, but at an ever-decreasing rate, asymptotically approaching zero velocity. Dark energy changes this picture completely by introducing a repulsive component to cosmic dynamics. And if dark energy maintains constant density as space expands, which is what a true cosmological constant would do, then as the universe grows larger, the total amount of dark energy increases while matter becomes more diluted, meaning that dark energy's influence grows ever stronger relative to matter's gravitational pull. Current observations suggest that we live in a universe where dark energy will continue to dominate and accelerate expansion forever, leading to a future where the space between galaxy clusters expands so rapidly that they lose all contact with each other, each cluster becoming isolated in an ever-growing bubble of space, eventually unable to see or communicate with other clusters because the space between them is expanding faster than light can traverse it. Over truly vast timescales measured in trillions of years, this accelerating expansion will carry even nearby galaxies beyond our cosmic horizon, making the universe appear increasingly empty from any vantage point, with only gravitationally bound structures like our local group of galaxies remaining visible, while everything else disappears beyond an ever-shrinking horizon. The acceleration caused by dark energy is gentle and patient, operating over billions of years, imperceptible in everyday life or even in the motions of planets and stars, but inexorable in its long-term consequences for cosmic structure and destiny. Understanding dark energy requires understanding the nature of vacuum itself and the relationship between quantum mechanics and gravity, two areas of physics that have not yet been successfully unified into a single coherent theory, making dark energy both an observational puzzle and a theoretical challenge that may require revolutionary new physics to fully explain. Magnetic fields, threading the cosmos, woven through the fabric of space like invisible threads connecting stars and galaxies. Magnetic fields represent another quiet giant that shapes cosmic evolution in subtle but important ways, guiding the motion of charged particles, channeling energy across vast distances, and influencing the formation of stars and the behavior of matter in extreme environments. Unlike gravity, which affects all matter equally, magnetic fields interact only with electrically charged particles and with other magnetic fields, creating a more selective but often very powerful influence on the plasma that makes up most of the visible matter in the universe. Stars, including our Sun, possess magnetic fields generated by the motion of electrically conducting material in their interiors. Swirling flows of hot plasma that act like natural dynamos, converting kinetic energy into magnetic energy through a process that remains not fully understood despite decades of research. These stellar magnetic fields extend outward from the star's surface into space, filling the surrounding region with invisible magnetic structures that guide the flow of the stellar wind, the continuous stream of charged particles that every star emits into its cosmic neighborhood, creating the heliosphere around our Sun and similar structures around other stars. The Sun's magnetic field is not static, but varies over an 11-year cycle during which the field's strength and configuration change dramatically, from relatively simple configurations during solar minimum to complex tangled arrangements during solar maximum, when the Sun is most active and produces the most solar flares and coronal mass ejections. These magnetic variations affect space weather throughout the solar system, influencing the intensity of cosmic rays that reach Earth and creating beautiful auroras when charged particles guided by Earth's magnetic field collide with atoms in the upper atmosphere. Planets can also possess magnetic fields if they have liquid conducting cores that rotate and generate dynamo action. And Earth's magnetic field has protected life on our planet's surface from harmful solar and cosmic radiation for billions of years, deflecting charged particles around the planet and creating the magnetosphere, a bubble in space carved out of the solar wind by the planet's magnetic pressure. Rivers of magnetism between stars. The space between stars within galaxies is not empty, but filled with very thin gas, and with magnetic fields that thread through this interstellar medium like a cosmic nervous system, organizing the flow of matter and energy and playing important roles in the life cycle of stars and in the structure of galaxies themselves. These interstellar magnetic fields are extremely weak compared to the fields near stars or planets, typically millions of times weaker than Earth's magnetic field at its surface. But they extend across such enormous volumes that their total influence is significant in shaping galactic dynamics. The fields form complex, three-dimensional structures, including ordered spiral patterns that follow the spiral arms of disk galaxies, vertical components that extend above and below the galactic plane, and tangled turbulent regions where the field lines twist and reconnect in intricate ways. Interstellar magnetic fields affect the motion of cosmic rays, the high-energy charged particles that zip through space at nearly the speed of light. causing these particles to spiral around magnetic field lines and preventing them from easily escaping the galaxy, effectively trapping cosmic rays within the galactic volume and making them much more important for the energy balance and chemistry of the interstellar medium than they would be if they could simply stream away into intergalactic space. The magnetic fields also provide support pressure that helps hold up giant molecular clouds against their own gravity, slowing the collapse that leads to star formation and changing the rate and efficiency with which gas is converted into stars, making magnetism an important factor in regulating galactic evolution over billions of years. When gas does collapse to form new stars, the magnetic fields threading through the collapsing cloud get dragged along with the material and compressed, becoming much stronger in the process. And these enhanced fields can launch powerful bipolar outflows and jets that carry away excess angular momentum and allow the forming star to continue accreting material, despite the rotational barrier that would otherwise prevent further collapse. Observations of polarized light from distant stars, light whose waves vibrate preferentially in certain directions because of scattering by magnetically aligned dust grains in the interstellar medium, allow astronomers to map the structure of galactic magnetic fields and to study how these fields relate to other properties like gas density, star formation activity, and galactic rotation. Magnetic fields, on cosmic scales, beyond individual galaxies, magnetic fields continue their invisible influence on even larger scales, permeating the space between galaxies within clusters and possibly extending along the filaments of the cosmic web that connects clusters across hundreds of millions of light years. These intergalactic magnetic fields are even weaker than interstellar fields, so tenuous that detecting them requires observing their effects on radio waves traveling from distant galaxies through the magnetized plasma filling the space between. But despite their weakness, they may play important roles in cosmic evolution by affecting the distribution of energy from active galaxies and by influencing the formation of large-scale structure. Galaxy clusters contain hot gas at temperatures of millions of degrees that emits X-rays and that carries embedded magnetic fields. And when the supermassive black holes at the centers of large galaxies become active and launch enormous jets of material and energy into the surrounding space, these jets plow through the cluster gas and drive shocks and turbulence that amplify and redistribute the magnetic fields, spreading them throughout the cluster volume. The origin of cosmic magnetic fields remains an open question, with theories proposing that weak seed fields could have been generated in the early universe through various processes and then amplified over billions of years through dynamo action and compression, or that fields could have been produced by the first stars and galaxies and then spread through space by galactic winds and jets, gradually filling the universe with a weak magnetized background. Measurements suggest that even the voids between galaxy clusters, the emptiest regions of space known to exist, may contain extremely weak magnetic fields, though detecting such fields pushes current technology to its limits and remains an active area of research. Understanding cosmic magnetism requires combining observations across many wavelengths from radio to gamma rays with sophisticated computer simulations that model how magnetic fields behave in the complex environments of galaxies and clusters, where they interact with gravity, gas dynamics, cosmic rays, and other phenomena in ways that can produce feedback loops and unexpected emergent behaviors. The solar wind's invisible stream, flowing outward from the sun at speeds of hundreds of miles per second. The solar wind is a continuous stream of charged particles, mainly protons and electrons, that carries magnetic field lines from the sun's surface out into the solar system and beyond, creating a dynamic environment that affects all the planets and that extends far beyond the orbits of the outer planets into interstellar space. The solar wind is not steady, but varies with solar activity. becoming stronger and more turbulent during periods of high solar activity, when the sun's magnetic field is most tangled, and when solar flares and coronal mass ejections inject additional material into the wind. These variations in the solar wind create space weather that can affect satellites and power grids on Earth, can influence the orbits of spacecraft, and can create beautiful auroras when energetic particles guided by Earth's magnetic field collide with atmospheric atoms and molecules. The boundary where the solar wind's pressure is balanced by the pressure of the surrounding interstellar medium is called the heliopause, and it defines the outer edge of the heliosphere, the bubble carved out by the sun in the local interstellar medium. Both Voyager spacecraft have crossed the heliopause and entered interstellar space, providing our first direct measurements of the conditions beyond the sun's immediate influence, and confirming that the heliosphere acts as a kind of shield that partially protects the inner solar system from the full intensity of galactic cosmic rays. The solar wind carries away not just particles, but also energy and angular momentum from the sun, representing a slow but steady loss of mass that will continue throughout the sun's life on the main sequence. Though the total amount lost over billions of years is small compared to the sun's total mass, understanding the solar wind and its interactions with planetary environments helps us understand space weather and space climate, the changing conditions in the near-Earth environment that can affect technology and human activities. And it provides insights into how other stars might affect their planetary systems through their own stellar winds. Cosmic rays, racing through space. Filling the galaxy with their invisible presence, cosmic rays are high-energy particles, mostly protons, but also heavier atomic nuclei and electrons, that speed through space at velocities approaching the speed of light, carrying energies that can exceed by billions of times the energies achieved in our most powerful particle accelerators here on Earth. These particles rain down constantly on Earth and all other objects in the solar system, passing through our bodies at a rate of several per second, usually without interaction, but occasionally colliding with an atomic nucleus and creating a cascade of secondary particles that can be detected at ground level. The origins of cosmic rays were mysterious for decades after their discovery. And even now, many questions remain about how particles are accelerated to such enormous energies and what proportion come from various sources, including supernova explosions, pulsar winds, active galactic nuclei, and possibly more exotic phenomena like the decay of dark matter particles. Supernova remnants, the expanding shells of gas and magnetic field created when massive stars explode, are thought to be the primary sources of cosmic rays, up to energies of about 10 to the 15th electron volts, which is already incredibly energetic, but still far below the highest energy cosmic rays observed. The acceleration process likely involves particles bouncing back and forth across the shock waves created by the expanding supernova remnant, gaining a little energy with each crossing through a process called diffusive shock acceleration. And after many crossings, a small fraction of particles can reach very high energies, while most particles remain at lower energies. The magnetic fields in supernova remnants play crucial roles in this acceleration by confining particles near the shock and by creating the turbulence necessary for the acceleration process to work efficiently. For the highest energy cosmic rays, those above 10 to the 18th electron volts and extending up to 10 to the 20 electron volts or even higher, supernova remnants cannot provide sufficient acceleration, and the sources remain uncertain, though candidates include active galactic nuclei powered by supermassive black holes, gamma-ray bursts from the collapse of massive stars, and other exotic high-energy phenomena in distant galaxies. Cosmic rays and galactic chemistry. Beyond their role as messengers carrying information about high-energy processes in the universe, cosmic rays also influence their environment in subtle but important ways, contributing energy to the interstellar medium, affecting the chemistry and ionization state of gas clouds, and even potentially influencing star formation rates and galactic evolution. When cosmic rays pass through the thin gas between stars, they can ionize atoms by knocking off electrons, and in the dense cores of molecular clouds, where starlight cannot penetrate, and where most other sources of ionization are absent. Cosmic rays provide the only significant source of ions and free electrons, making them crucial for maintaining the minimal level of ionization necessary for magnetic fields to couple to the gas and for certain chemical reactions to proceed. This ionization by cosmic rays affects the formation of molecules in space, including water and organic compounds. Because the chemistry that builds complex molecules from simpler atoms often requires charged particles to facilitate reactions that would not occur between neutral atoms alone. Cosmic rays also deposit energy into the interstellar medium through their occasional collisions with gas atoms, heating the gas and providing pressure support that can resist gravitational collapse, potentially affecting how efficiently gas clouds form stars and how the rate of star formation varies across different regions of galaxies. The spectrum of cosmic rays, the distribution of particles at different energies, follows a power law with many low-energy particles and progressively fewer particles at higher energies. And this shape provides clues about acceleration mechanisms and propagation effects, but also means that most of the energy and most of the influence comes from relatively low-energy cosmic rays, rather than from the rare ultra-high energy particles that capture public imagination. Cosmic rays cannot travel in straight lines through the galaxy because they are charged particles, and the galactic magnetic field causes them to spiral and scatter, making their paths through space resemble random walks rather than straight trajectories. And this means that cosmic rays take much longer to traverse the galaxy than light does, spending millions of years bouncing around between magnetic field fluctuations before eventually escaping into intergalactic space or being absorbed by collisions with gas atoms. The pressure of starlight. Light itself exerts pressure when it strikes matter, a fact that seems counterintuitive because light appears weightless and insubstantial. But photons carry momentum, and when they are absorbed or reflected by an object, they transfer that momentum, creating a tiny force that over time and distance can have significant effects on small particles and on the dynamics of astrophysical systems. Radiation pressure from starlight is negligible for large objects like planets, where gravity dominates completely. But for tiny dust grains, smaller than a micron, and for atoms and molecules in hot ionized gas, radiation pressure can be comparable to or even greater than gravitational attraction, fundamentally affecting how these small particles move and how they are distributed through space. Around very luminous stars, particularly massive hot stars that produce enormous amounts of ultraviolet radiation, the outward pressure of starlight on gas atoms can drive powerful stellar winds that carry away mass from the star at rates of millions of times the sun's relatively gentle solar wind, and these radiation-driven winds are responsible for the beautiful nebulae that surround dying massive stars and for the chemical enrichment of galaxies as stellar processed material is ejected into the interstellar medium. In the formation of stars, radiation pressure from the growing protostar at the center of a collapsing cloud can halt or reverse infall, creating an upper limit to stellar masses because stars much above 100 times the mass of the Sun would produce so much radiation pressure that they could not accrete additional material and might even blow themselves apart through radiation-driven instabilities. Dust grains in the inner regions of protoplanetary disks around young stars feel radiation pressure pushing them outward, while gravity and friction with gas pull them inward. And the balance between these forces affects how dust moves through the disk and how it can collide and stick together to begin building larger bodies that eventually become asteroids and planets. On cosmic scales, radiation pressure is relatively unimportant compared to gravity for determining large-scale structure. But in certain environments, like near-active galactic nuclei, where supermassive black holes are actively accreting matter and producing enormous luminosities, radiation pressure can drive galactic-scale winds that expel gas from the galaxy entirely, affecting star formation and galactic evolution. Tidal forces reshaping worlds. Though gravity itself pulls objects together uniformly, differences in gravitational strength across an extended object create tidal forces that stretch and squeeze matter in ways that can dramatically reshape planets, moons, stars, and even entire galaxies over long periods of time. Tidal forces arise because gravity weakens with distance, following an inverse square law, which means that the side of an object closer to a massive body feels stronger gravitational pull than the far side. And this difference in pull creates a stretching force along the line, connecting the two objects, and a compression force perpendicular to that line. On Earth, we experience tides in the oceans as the moon's gravity pulls more strongly on the water on the side facing the moon than on the solid Earth beneath, or on the water on the opposite side, creating two tidal bulges that rotate around the planet as Earth spins, producing the twice-daily pattern of high and low tides that has shaped coastal ecosystems and human maritime activities for millennia. Tidal forces are weak for objects at large distances or for small objects, but they grow stronger as objects get closer together or as the sizes of the objects increase. And they can become strong enough to tear objects apart if the tidal gradient exceeds the internal forces holding the object together. When a moon or asteroid approaches a planet too closely, crossing the Roche limit where tidal forces exceed the object's gravitational self-binding, the object will be torn apart into a ring of debris. And this process created the beautiful rings of Saturn and the other giant planets, though maintaining those rings requires ongoing replenishment from impacts on moons and from other processes. Tidal forces also transfer energy and angular momentum between objects, causing moons to gradually spiral either toward or away from their parent planets, depending on the configuration of the system, and causing planets and moons to slowly spin down until they become tidally locked with one side permanently facing their partner. Earth's moon is tidally locked to Earth, always showing the same face toward our planet because its rotation period equals its orbital period, a condition that developed over millions of years as tidal friction gradually slowed the moon's spin until it matched its orbit. The energy dissipated by tidal friction heats the interiors of moons and planets. And this tidal heating is particularly important for moons of the giant planets like Jupiter's Europa and Saturn's Enceladus, where the continuous squeezing and stretching as they orbit in elliptical paths generates enough heat to maintain liquid water oceans beneath their icy surfaces, despite being far from the sun, where temperatures would otherwise keep everything frozen solid. Tidal disruption in the cosmos. On cosmic scales beyond planetary systems, tidal forces continue their patient work of reshaping matter and transferring energy, affecting interactions between galaxies, between stars, and even between black holes and stars or planets that venture too close to their intense gravitational fields. When two galaxies approach each other during what will likely become a merger over hundreds of millions of years, the tidal forces from each galaxy begin pulling on the stars and gas in the other galaxy long before the main bodies actually interpenetrate, drawing out long tidal tails and bridges of stars that stretch across hundreds of thousands of light years, creating some of the most beautiful and dramatic structures visible in deep space photographs. These tidal streams, pulled from both galaxies by their mutual gravitational attraction, eventually either fall back into the merged galaxy or are flung out into intergalactic space to wander between galaxy clusters as orphaned stellar populations disconnected from any galactic home. The collision and merger of galaxies sounds like it should involve many individual collisions between stars, but the space between stars within galaxies is so vast that direct stellar collisions are extremely rare, even when entire galaxies pass through each other. And instead, the main effects come from gravitational interactions and tidal forces acting collectively on billions of stars simultaneously, and from compression of interstellar gas that triggers waves of star formation and feeds material toward the supermassive black holes at the galactic centers. When a star approaches too close to a supermassive black hole, close enough that the tidal force from the black hole's enormous gravity exceeds the star's self-gravity, the star is stretched into a long, thin stream in a process called tidal disruption, with the inner part of the stream falling into the black hole, while the outer part may escape back into space. These tidal disruption events produce brief but enormous releases of energy as the disrupted stellar material heats up while spiraling into the black hole, creating flares that can briefly outshine entire galaxies and that provide opportunities to detect supermassive black holes that were previously quiescent and invisible. Binary star systems, pairs of stars orbiting each other, also experience tidal forces when the stars are close enough. And these forces can transfer angular momentum between the star's orbital motion and their rotation, eventually causing the stars to become tidally locked to each other the way the moon is locked to Earth, and can transfer mass from one star to the other if tidal forces distort one star enough that its outer atmosphere overflows onto its companion. Neutrinos ghosting. Through everything among the most elusive particles in the universe, neutrinos are nearly massless, electrically neutral particles that interact so weakly with ordinary matter that they can pass through the entire Earth with almost no chance of being absorbed or deflected, making them invisible messengers that carry information from the most extreme environments in the cosmos directly to our detectors without being blocked or distorted by intervening material. Neutrinos are produced in enormous numbers by nuclear reactions in stars, by supernova explosions, by cosmic ray interactions in the atmosphere, and by natural radioactive decay in Earth's crust and oceans. And they stream through space at nearly the speed of light, crossing the galaxy without knowing or caring about the planets and dust clouds and gas that would block or absorb light and other electromagnetic radiation. The Sun produces about 10 to the 38th neutrinos every second through the nuclear fusion reactions in its core that convert hydrogen to helium and release energy. And these neutrinos escape from the Sun's center immediately without delay, carrying away a small fraction of the fusion energy. Whereas the photons produced by the same reactions take hundreds of thousands of years to random walk their way from the core to the surface, because they are constantly absorbed and re-emitted by atoms in the dense solar interior. Trillions of solar neutrinos pass through your body every second, day and night, regardless of whether the Sun is above or below the horizon, streaming through Earth as if our planet were not there. And almost all of them pass through without interacting with a single atom in your body or anywhere else, continuing their journey out into the galaxy. Detecting neutrinos requires building massive underground detectors containing thousands of tons of ultra-pure water or other material, and watching for the extremely rare occasions when a neutrino does interact with an atomic nucleus, producing secondary particles that create flashes of light in the detector. And even these huge detectors catch only a tiny fraction of the neutrinos passing through them, perhaps a few dozen per day from all sources combined. Despite their elusiveness, neutrinos are important because they provide unique information about processes occurring in environments we cannot observe in any other way, including the cores of stars where fusion occurs, the interiors of supernova explosions in the first seconds after core collapse, and possibly the Big Bang itself, if we could detect the cosmic neutrino background, predicted to exist similarly to the cosmic microwave background, but at much lower energies. The neutrinos, subtle dance neutrinos, come in three types or flavors called electron neutrinos, muon neutrinos, and tau neutrinos, named after the three types of charged leptons with which they are associated. And one of the most surprising discoveries about neutrinos is that they can change flavor as they travel through space, transforming from one type to another through a quantum mechanical process called neutrino oscillation. This flavor transformation occurs because the three neutrino flavors are not actually eigenstates of mass, but rather quantum superpositions of three mass eigenstates, meaning that a neutrino created as an electron neutrino is actually a mixture of three different mass states. And as the neutrino travels through space, these mass components oscillate in their quantum phases relative to each other, causing the flavor composition to change periodically. Neutrino oscillation was discovered by observing that fewer electron neutrinos arrive from the Sun than theoretical models predict should be produced in the solar core. A discrepancy called the solar neutrino problem that puzzled physicists for decades until they realized that some of the electron neutrinos were transforming into muon and tau neutrinos during their journey from the Sun's core to Earth. And since the early detectors were only sensitive to electron neutrinos, they missed the neutrinos that had changed flavor. The fact that neutrinos oscillate between flavors proves that neutrinos must have mass, even if that mass is extremely small, because massless particles could not exhibit the oscillation behavior. And this discovery of neutrino mass was the first clear evidence for physics beyond the standard model of particle physics, which had assumed neutrinos were massless. The masses of neutrinos are not yet known precisely, but are constrained to be less than about 1 electron volt, more than 500,000 times lighter than an electron, making them by far the lightest massive particles known. Yet because neutrinos are so abundant in the universe, with hundreds of neutrinos per cubic centimeter left over from the Big Bang, their tiny masses add up to a significant contribution to the total mass of the universe, though not enough to account for dark matter. Understanding neutrino properties, including their masses, the mixing angles that determine how they oscillate between flavors, and whether they are their own antiparticles through a special property called Majorana nature, remains an active area of research with important implications for particle physics, cosmology, and our understanding of why the universe contains more matter than antimatter, vacuum energy, and quantum fields. Even in the complete absence of matter and radiation, even in the perfect vacuum of empty space far from any galaxy or star, space itself is not truly empty, but filled with quantum fields that permeate all of existence and that give rise to all the particles and forces we observe in nature when these fields are excited or disturbed. This concept of quantum fields as the fundamental constituents of reality represents a profound shift from thinking about particles as the primary entities to thinking about fields as primary and particles as secondary manifestations or excitations of those fields. The electromagnetic field exists everywhere, even where there are no photons. The electron field exists everywhere, even where there are no electrons. And similarly for all other particles and forces, creating an invisible infrastructure of potential from which actual particles and interactions emerge when energy and circumstances are appropriate. These quantum fields are not static or quiet, but constantly fluctuate at very small scales and for very short times, creating what are called virtual particles that pop into existence from the vacuum and then annihilate and disappear so quickly that they do not violate conservation of energy, allowed by the quantum uncertainty principle that permits temporary violations of energy conservation for times too brief to measure. These vacuum fluctuations are not just mathematical artifacts, but have real measurable effects, including the Casimir effect, where two closely spaced metal plates experience a tiny attractive force, because the vacuum fluctuations between the plates are restricted compared to the fluctuations outside the plates, creating a pressure difference that pushes the plates together. The vacuum fluctuations also cause small shifts in the energy levels of atoms, called Lamb shifts, that can be measured with high precision and that agree perfectly with theoretical calculations, providing strong evidence that the quantum vacuum is indeed seething with activity, even though it appears completely empty to our senses. The energy density of the vacuum fluctuations, if naively calculated using quantum field theory, comes out to be absurdly large, larger than the observed energy density of the universe by a factor of 10 to the 120 or more, creating what physicists call the cosmological constant problem, or the vacuum catastrophe. One of the most severe disagreements between theory and observation in all of science. The Higgs field's universal presence, filling all of space uniformly and permanently, never turning off or becoming absent anywhere. The Higgs field represents a unique type of quantum field that, unlike all others, maintains a non-zero value, even in its lowest energy state or vacuum configuration. And it is this non-zero vacuum value that gives mass to fundamental particles through their interactions with the field. Most quantum fields have vacuum values of 0, meaning that in the absence of excitations or particles, the field strength is 0 everywhere. But the Higgs field settled into a non-zero vacuum state shortly after the Big Bang, when the universe cooled enough, and it has maintained this non-zero value throughout all subsequent cosmic history. Particles acquire mass by interacting with this omnipresent Higgs field as they move through space, with particles that interact more strongly, experiencing more resistance to acceleration and therefore appearing more massive, while particles that do not interact with the Higgs field at all remain massless and travel at the speed of light, like photons. The strength of each particle's interaction with the Higgs field determines its mass, with heavy particles like the top quark strongly coupled to the field and light particles like electrons weakly coupled. And this provides an elegant explanation for why different particles have different masses, a pattern that otherwise appears arbitrary and unexplained. The discovery of the Higgs boson particle at the Large Hadron Collider in 2012 provided direct confirmation that the Higgs field exists. Because the Higgs boson represents an excitation or quantum of the Higgs field, similar to how a photon represents an excitation of the electromagnetic field. And finding this particle proved that the field is real, and that the mechanism by which it gives mass to particles operates as theory predicted. The Higgs field's non-zero vacuum value raises deep questions about why the field settled into this particular state, rather than remaining at 0 like other fields, and whether the Higgs field might be unstable over very long timescales, potentially billions or trillions of years, possibly transitioning to a lower energy state in a process that would fundamentally change the properties of particles and make the universe inhospitable to life as we know it. Though calculations suggest this is either impossible or would take far longer than the current age of the universe to occur. The fabric of spacetime at smallest scales. As we examine spacetime at smaller and smaller scales, approaching distances of about 10 to the minus 35 meters called the Planck length, and times of about 10 to the minus 43 seconds called the Planck time, we reach a regime where quantum mechanics and gravity become equally important, and where our current theories of physics break down, unable to describe what happens because we lack a complete theory of quantum gravity that consistently combines the principles of quantum mechanics with the geometry of general relativity. At these incredibly tiny Planck scales, quantum fluctuations in the geometry of space-time itself become important, causing space and time to fluctuate and foam in a quantum uncertainty that makes the classical smooth space-time of general relativity only an approximation valid at larger scales. These quantum fluctuations of geometry might cause space-time to have a discrete or foamy structure at the smallest scales rather than being infinitely divisible and smooth. With the Planck length representing a fundamental minimum meaningful distance below which the concept of distance itself becomes fuzzy and uncertain. and the Planck time representing a fundamental minimum meaningful duration, below which the concept of time loses its usual meaning. Several approaches to quantum gravity, including string theory and loop quantum gravity, propose specific structures for space-time at Planck scales, with string theory suggesting that space-time has extra dimensions beyond the four we experience, and that fundamental entities are not point particles, but tiny vibrating strings. While loop quantum gravity suggests that space is quantized into discrete elementary volumes, connected in a network-like structure. These theories remain speculative because the Planck scale is far beyond anything we can directly probe with experiments, being about 20 orders of magnitude smaller than the smallest distances we can access at particle colliders. But studying quantum gravity is essential for understanding the very early universe in the first tiny fraction of a second after the Big Bang, when the entire observable universe was compressed into a volume smaller than the Planck length. And for understanding the interiors of black holes where quantum gravity effects should dominate. The unification of quantum mechanics and gravity represents one of the great outstanding challenges in theoretical physics, requiring new mathematical frameworks and possibly profound revisions to our concepts of space and time. And success in this endeavor would represent a fundamental advance in human understanding of nature at its deepest level. The arrow of time's gentle flow. Among the invisible forces shaping the universe, time itself flows in one direction only, from past to future, creating an arrow of time that seems fundamental to our experience, yet that appears nowhere in the basic laws of physics, which are almost all time symmetric and work equally well whether time runs forward or backward. The thermodynamic arrow of time, the direction in which entropy or disorder increases, points from ordered states to disordered states, from low entropy configurations to high entropy configurations, creating the familiar progression from structured, organized systems to more random, disorganized systems that we observe throughout nature. This increase in entropy is not absolute but statistical, representing what is overwhelmingly probable rather than what is strictly required. Because at the microscopic level, the motions of individual particles are reversible and could in principle run backward. But the number of possible disordered configurations vastly exceeds the number of ordered configurations, making the spontaneous decrease of entropy fantastically unlikely in any system containing large numbers of particles. The arrow of time is intimately connected to the initial conditions of the universe, to the fact that the Big Bang appears to have started in an extremely low entropy state, with matter and energy distributed very uniformly and with very specific conditions that have not yet been fully explained. And as the universe evolved, this initial low entropy has been steadily increasing, spreading disorder throughout cosmic space, while locally creating islands of order like stars and galaxies and living things at the expense of greater disorder elsewhere. Time's flow creates the possibility of causation, of cause preceding effect, of events being influenced by their past but not by their future, establishing the temporal structure that makes narrative and memory and planning possible. And yet, the fundamental origin of time's arrow remains mysterious and the subject of ongoing research and debate. Some physicists suggest that the arrow of time emerges from quantum mechanics and the process of wave function, collapse or decoherence that occurs when quantum systems interact with their environments, irreversibly transforming quantum superpositions into classical definite states. While others argue that the arrow is cosmological in origin and requires explaining the special initial state of the universe. The gentle flow of time carries everything forward without exception, transforming potential into actual, converting energy from useful forms to waste heat, increasing the universe's total entropy, moving irreversibly from the low entropy beginning toward a high entropy future, and creating the subjective experience of time passing that is so central to conscious experience yet so difficult to capture in physical equations. The symphony of invisible forces. As we drift deeper into understanding these quiet giants, we begin to appreciate how the invisible forces we have explored do not act in isolation, but interact with each other in complex ways, creating feedback loops and emergent behaviors that shape cosmic evolution through their combined effects rather than through any single force acting alone. Gravity gathers matter into structures. Compression heats that matter and triggers nuclear fusion. Fusion produces radiation that creates pressure, pushing outward against gravity. Stellar winds and supernova explosions driven by radiation pressure and nuclear energy disperse heavy elements and magnetic fields into the interstellar medium. Those magnetic fields affect the collapse of new generations of gas clouds. Cosmic rays accelerated by shocks in supernova remnants ionize molecular clouds and influence their chemistry. Dark matter provides the gravitational scaffolding that guides where normal matter accumulates. And dark energy determines the ultimate fate of all these structures by controlling the global expansion of space. These interactions create a cosmic ecosystem where cause and effect flow in multiple directions simultaneously, where small changes can amplify through feedback into large consequences, and where the whole becomes greater than the sum of its parts through emergent complexity. The formation of galaxies illustrates this interplay beautifully, beginning with tiny quantum fluctuations in the density of the early universe that were amplified by dark matter's gravity, drawing in normal matter that heated up and formed the first stars, those stars exploding and enriching their surroundings with heavy elements and magnetic fields. Subsequent generations of stars forming from this enriched material with different properties, stellar evolution and supernova explosions regulating further star formation through energy injection into the interstellar medium. And all of this occurring within the context of dark energy's gradual acceleration of cosmic expansion that affects when and how structures can form. Understanding any one of these forces or phenomena requires understanding its context, its interactions with other forces, its feedbacks, and its emergent properties, making cosmic evolution a true symphony where every instrument matters and where removing any one element would change the entire composition fundamentally. The universe reveals itself as deeply interconnected through these invisible forces, with no part truly independent from the whole. No process occurring in isolation from all others, creating a unity underlying the apparent diversity of cosmic phenomena that scientists strive to capture in unified theories and comprehensive models. Measuring the invisible, the quiet giants that shape our universe, cannot be observed directly with human senses, requiring sophisticated instruments and clever techniques to detect their presence and measure their properties. And the history of physics and astronomy is largely the history of finding ways to make the invisible visible and the intangible measurable. Gravity reveals itself through the motions of objects falling to Earth, orbiting in space, and bending the paths of light. And by carefully measuring these motions, we infer the gravitational field's strength and map its distribution through space, detecting dark matter through its gravitational effects and testing general relativity through precise measurements of orbits and light deflection. Magnetic fields show themselves through their effects on charged particles and polarized light, with radio telescopes detecting synchrotron radiation from electrons spiraling in magnetic fields, optical telescopes observing the polarization of starlight by magnetically aligned dust grains, and spacecraft instruments measuring fields directly in the space environment near Earth and other planets. Neutrinos interact so rarely that detecting them requires massive instruments deep underground, shielded from cosmic rays, watching enormous volumes of ultra-pure material for the telltale flashes of light produced when a neutrino occasionally interacts with an atomic nucleus. And even then, catching only a tiny fraction of the neutrinos passing through. Gravitational waves required building instruments so sensitive that they could detect changes in distance smaller than an atomic nucleus across measuring arms several miles long, using laser interferometry and sophisticated signal processing to extract the faint oscillating signature of gravitational waves from noise and to distinguish them from vibrations caused by earthquakes, traffic, weather, and countless other environmental disturbances. Dark energy manifests only in its effects on cosmic expansion, measurable through observations of distant supernova and through detailed mapping of the cosmic microwave background, requiring decades of careful observations and analysis to establish its existence beyond doubt. Each of these measurement techniques represents a triumph of human ingenuity and persistence, finding ways to detect phenomena that are invisible and that often eluded detection for decades or centuries, because the required sensitivity seemed impossible to achieve with available technology. The development of new detection methods often leads to unexpected discoveries, as instruments built to measure one thing reveal other phenomena that were completely unanticipated. And this pattern suggests that there may be other quiet giants still waiting to be discovered, forces or phenomena that we have not yet imagined, or that our current instruments cannot detect. The future of invisible architecture. As our instruments become more sensitive and our theories more sophisticated, we continue to probe deeper into the nature of the invisible forces shaping the cosmos, seeking to understand dark matter and dark energy more completely, to detect primordial gravitational waves from the Big Bang itself, to measure cosmic magnetic fields in the voids between galaxy clusters, to detect the cosmic neutrino background left over from the early universe, and to test whether additional forces or particles beyond those in the standard model of particle physics might exist. Future gravitational wave detectors, including space-based observatories, will open new windows on the universe by detecting lower frequency gravitational waves from supermassive black hole mergers and from other sources invisible to current ground-based detectors, providing information about cosmic history and extreme gravity that cannot be obtained any other way. Next-generation neutrino telescopes will detect neutrinos from distant galaxies and from the early universe, tracing the history of star formation and revealing the workings of the most violent explosions in the cosmos. New dark matter experiments deploying increasingly sensitive detectors deep underground and at the Large Hadron Collider search for direct evidence of dark matter particles and for signs of the physics beyond the standard model that must exist to explain dark matter's nature. Future space missions will map cosmic magnetic fields with unprecedented detail and sensitivity, revealing how magnetism threads through the cosmic web and influences structure formation on the largest scales. Improved measurements of dark energy through multiple independent techniques, including supernovae, Baryon acoustic oscillations, and gravitational lensing, will determine whether dark energy is truly a cosmological constant, or whether it varies with time and space in ways that might provide clues to its fundamental nature. These investigations will occupy astronomers and physicists for decades to come, gradually filling in our understanding of the invisible forces and revealing whether we have correctly identified all the major players in cosmic evolution, or whether surprises still await discovery. The quest to understand these quiet giants represents humanity's deepest questions about the nature of reality, about what exists and how it works, about the hidden architecture that makes the visible universe possible. And each advance in this understanding represents a step toward a more complete and more unified picture of nature at its most fundamental level. The philosophy of the unseen, the existence of invisible forces that shape reality without being directly perceivable, raises profound philosophical questions about the nature of existence, about what it means to be real, about the relationship between observation and reality, and about the limits of human knowledge. For most of human history, reality was equated with what could be directly observed through the senses. with seeing being believing, and with invisible entities regarded with suspicion as possibly imaginary or supernatural. But modern physics has revealed that most of what is real cannot be directly sensed, and that the visible material world emerges from an invisible foundation of fields and forces and quantum possibilities. This shift from a sensory-based ontology to a mathematical theoretical ontology represents a profound change in how we understand existence. Accepting the reality of entities and phenomena that we know about only through their indirect effects and through the mathematical structures that describe them. Dark matter and dark energy cannot be seen or touched, yet they make up 95% of the universe's content. Quantum fields cannot be observed directly, yet all of material reality consists of excitations of these fields, and space-time itself cannot be perceived as such. Yet it provides the stage on which all events unfold, and its curvature determines how objects move and light propagates. Accepting the reality of the unseen requires trust in the scientific method, in the power of mathematical reasoning, in the reliability of instruments that extend our senses far beyond their natural range, and in the collective judgment of the scientific community that validates or rejects theoretical proposals based on how well they predict observations and explain phenomena. This trust is not blind faith, but is based on the remarkable track record of science in discovering hidden aspects of nature and using that knowledge to develop technologies that work, demonstrating that our mathematical descriptions of invisible forces correspond to something real, even if we cannot directly perceive what that something is. The invisible forces remind us of the limits of human perception and human intuition, showing that reality extends far beyond what we can sense directly, and that understanding nature requires methods and mathematics that often contradict common sense and everyday experience. They also remind us that much remains unknown and possibly unknowable, that our current theories may be incomplete or incorrect in ways we have not yet discovered, and that humility is appropriate when contemplating the vast cosmos with our limited perspective and finite understanding. Quiet giants and human understanding. The story of discovering and understanding the invisible forces that shape the universe is also a story about human creativity and persistence, about the generations of scientists who contributed pieces to a vast puzzle without seeing the complete picture, about the development of mathematics sophisticated enough to describe nature's hidden workings, and about the philosophical shifts required to accept realities that contradicted intuition and common sense. From Newton's insight that the same force pulling an apple toward Earth also holds planets in their orbits, to Einstein's revolutionary reconception of gravity as space-time geometry, to the development of quantum field theory that describes reality in terms of fields and excitations rather than particles and forces, to the ongoing struggles to understand dark matter and dark energy. The history of physics is a history of making the invisible visible and the abstract concrete through imagination, disciplined by mathematics and tested by observation. This process requires unusual combinations of skills and attitudes, including mathematical ability to work with abstract structures, physical intuition to guess what nature might be doing behind the scenes, experimental skill to design instruments that can test theoretical predictions, openness to radical new ideas that contradict established beliefs, skepticism to avoid accepting unproven claims, and patience to work for decades on problems that may not be solved in a single lifetime. The invisible forces have been revealed through collaborations among thousands of scientists working across generations, each contribution building on previous work and enabling future discoveries in a cumulative process that gradually expands human knowledge outward from familiar territory into increasingly strange realms where intuition fails and only mathematics and careful reasoning can guide us. The development of general relativity illustrates this process beautifully. beginning with Einstein's realization that gravity might be understood as space-time curvature, requiring years of struggle to learn the necessary mathematics of differential geometry and to formulate equations that correctly describe this curvature, followed by decades of theoretical work by many physicists to understand the implications and predictions of the theory. And finally, by increasingly sophisticated observational tests using precision timing of pulsars, gravitational lensing by galaxies, detection of gravitational waves, and other techniques that confirm the theory's predictions with remarkable accuracy. Each invisible force has a similar story of gradual discovery and understanding. And each story reminds us that knowledge progresses through the collaborative efforts of many people over long periods, with false starts and mistakes and controversies along the way, but ultimately converging on deeper and more accurate descriptions of nature's workings. The universe's gentle teaching. The quiet giants teach us patience, showing through their own slow, steady operation across billions of years that understanding comes gradually through persistent effort and cannot be rushed or forced. Gravity shapes galaxies over hundreds of millions of years. Dark energy accelerates cosmic expansion over billions of years. Magnetic fields evolve through galactic dynamos, operating over countless rotations. And cosmic rays scatter through the galaxy for millions of years before escaping or being absorbed. These vast timescales remind us that nature operates according to its own schedule without regard for human impatience, and that some truths reveal themselves only to those willing to wait and to observe carefully over long periods. The invisible forces also teach us about interconnection and emergence, showing that complex behavior arises from the interactions of simpler components, and that understanding any phenomenon requires understanding its context and its relationships to other phenomena. No force acts in true isolation. No particle exists independent of the quantum fields permeating space. No structure forms without being shaped by multiple competing and cooperating influences. This holistic, interconnected nature of reality challenges reductionist approaches that seek to understand wholes by analyzing parts in isolation, suggesting that while such analysis is useful and necessary, it must be complemented by synthesis that reunites the parts and studies their interactions to understand how wholes emerge with properties that their components alone do not possess. The invisible forces teach us epistemic humility, reminding us how much of reality is hidden from direct observation and how our theories, while powerful and accurate within their domains, may be incomplete or incorrect in ways we have not yet discovered. Dark matter and dark energy together make up 95% of the universe, yet we do not know what they are. Quantum mechanics works perfectly for predictions, yet offers no clear picture of what is really happening between measurements. And our attempts to combine quantum mechanics with general relativity have not yet succeeded despite decades of effort by brilliant theorists. These limitations remind us that human knowledge is provisional and incomplete, that certainty is rare in science, and that healthy skepticism combined with openness to evidence is the appropriate attitude toward both established theories and new proposals. As you rest now and let these thoughts settle gently into deeper awareness, allow yourself to feel connected to these invisible forces that have shaped cosmic history and that continue their patient work in this present moment, pulling and pushing, bending and flowing, creating and destroying in the eternal dance of matter and energy through space and time. Drifting into cosmic sleep. Now, as we approach the end of our gentle exploration of the quiet giants, let us drift slowly and peacefully into even deeper contemplation of these invisible forces, allowing our thoughts to become as diffuse and subtle as the dark matter halos surrounding galaxies, as patient as gravity gathering matter over billions of years, as quiet as the vacuum seething with quantum fluctuations in the space between atoms. The invisible forces continue their work whether we observe them or not, whether we understand them or not, operating according to laws that existed before consciousness arose in the universe, and that will continue after all consciousness has faded away, shaping reality through their quiet, persistent influence that asks nothing from us except perhaps our wonder and our willingness to contemplate mysteries that dwarf all human concerns. In this moment of rest, you are held by these forces just as everything is held, supported by the solidity that emerges from quantum fields, pulled gently toward Earth's center by gravity, protected from cosmic radiation by magnetic fields, bathed in neutrinos streaming from the sun and from distant supernovae, existing within the gentle accelerations of dark energy, expanding space around you, though at scales so vast that you notice nothing in your immediate surroundings. You are part of the cosmic dance of invisible forces, not separate from them, but woven into their patterns, made of matter that once floated freely in space before gravity gathered it into clouds and then into stars, where fusion created the heavy elements that eventually came together to form planets and living things. The quiet giants shaped your ancestors over billions of years through their influence on cosmic and biological evolution, and they shape your present through every breath and heartbeat and thought, and they will shape the future long after your brief moment has passed, continuing their patient work of building structure and spreading entropy, of creating complexity from simplicity and order from chaos, operating in the darkness and silence with a steadiness that makes them trustworthy companions in the long journey of existence. Let yourself feel held by these invisible hands, supported by forces you cannot see, but that are no less real for their invisibility, cradled in the geometry of space-time, floating in the quantum foam, drifting through fields that permeate all space, moving slowly toward sleep as particles move toward equilibrium, as systems move toward maximum entropy, as tension flows toward release and awareness flows toward rest. The eternal presence of invisible forces. And so we complete our journey through the realm of the quiet giants, having explored together the invisible forces that shape everything from atoms to galaxies, and from the smallest quantum fluctuations to the largest cosmic structures spanning billions of light years. We have discovered that most of reality is hidden from direct observation, that the visible material world emerges from an invisible foundation of forces in fields and geometric relationships, and that understanding nature requires extending our perception beyond the narrow range of human senses into realms accessible only through instruments and mathematics. Gravity continues its patient work of gathering matter and curving space-time. Dark matter provides invisible scaffolding for visible structures. Dark energy accelerates cosmic expansion toward an isolated future. Magnetic fields thread through space, guiding charged particles and shaping astrophysical phenomena. Cosmic rays race through the galaxy, carrying messages about violent events. Neutrinos ghost through everything, providing unique windows on stellar cores and supernova explosions. Radiation pressure shapes stellar winds and limits stellar masses. Tidal forces reshape worlds and galaxies through differential gravity. Quantum fields fluctuate in the vacuum, making empty space alive with potential. And time flows in one direction, only carrying everything forward from past to future. These forces work together in complex interacting systems where feedback and emergence create behaviors that cannot be predicted by understanding each force in isolation, creating the rich diversity of phenomena we observe, from the formation of stars and galaxies to the chemistry of interstellar clouds to the evolution of structure across cosmic history. The quiet giants have operated since the beginning of time and will continue until the end, if such an end exists. Patient and persistent, asking nothing, giving everything, creating the conditions that make existence possible, and that allow complexity and consciousness to briefly arise in certain favorable corners of an otherwise mostly empty and dark universe. As you rest now in the gentle embrace of these invisible forces, knowing that you are always held by gravity, always surrounded by quantum fields, always bathed in neutrinos and cosmic rays and the faint whisper of the cosmic microwave background. Let yourself settle into the deep peace that comes from understanding your place in this vast cosmos, connected to everything through invisible threads that link you to the most distant galaxy and to the earliest moments after the Big Bang. Sleep now with the quiet giants. Rest in their eternal presence, and know that tomorrow, when you wake, the forces will still be there, still working their patient magic, still shaping the universe with invisible hands, still worthy of wonder and worthy of study, still holding mysteries that invite exploration, and still offering insights that deepen understanding of this strange and beautiful cosmos we briefly inhabit. The invisible forces endure, the quiet giants persist, and in their patient, steady operation across time and space, they teach us that some things are too subtle to see, but too important to ignore, too quiet to hear, but too powerful to resist, too mysterious to fully understand, but too fundamental to ever dismiss. Rest now in that knowledge, sleep now in that peace. And let the invisible architecture of reality support you completely as you drift into dreams where the boundaries between seen and unseen, between known and unknown, between self and cosmos gently dissolve into the unified whole from which all things emerge and to which all things return. Gravity, the silent architect of the cosmos. When you look up at the night sky, the patterns of stars and the slow drift of planets can seem peaceful and almost static. Yet behind that quiet appearance is a relentless, invisible influence that never stops working. Gravity is the force that shapes the universe on its largest scales. It pulls matter together, sculpts galaxies, binds planets to stars, and guides the paths of comets and clusters. It is everywhere, affecting everything with mass, but it never flashes or sparkles. It has no color, no sound, and no surface. It is simply there, persistent and patient, slowly arranging the cosmos over billions of years. This quiet persistence makes gravity one of the true giants of space, unseen and yet impossible to escape. The modern story of gravity begins with a simple idea. Every object with mass attracts every other object with mass. Isaac Newton's law of universal gravitation turned falling apples and orbiting moons into different expressions of the same underlying rule. According to Newton, the strength of the gravitational pull between two objects depends on their masses and the distance between them. Double the distance, and the force drops dramatically. Bring objects closer, and the attraction increases. With this deceptively simple formula, Newton could explain why the moon remains bound to Earth instead of flying off into space, and why the planets trace out their elegant paths around the sun. For the first time, the motions in the heavens and the motions on Earth were joined by a single mathematical description. Still, Newton's gravity was a kind of action at a distance. One mass seemed to reach across empty space and tug on another instantly, with no medium or mechanism in between. For centuries, this worked extremely well as a predictive tool, but it left a nagging conceptual gap. In the early 20th century, Albert Einstein approached the question from a different angle and transformed our understanding of what gravity actually is. In his general theory of relativity, gravity is not a force in the usual sense, but the curvature of space and time themselves. Massive objects, like stars and planets, do not pull on things through some invisible string. Instead, they warp the fabric of space-time, and other objects move along the curved paths created by that warping. One way to picture this is to imagine a heavy ball resting on a stretched rubber sheet. The ball creates a dent in the sheet, and when you roll smaller marbles nearby, their paths bend around the indentation. The marbles are not being pulled by a force reaching out from the ball. They are simply following the curved surface. In a similar way, the sun creates a deep well in space-time, and the planets follow curved trajectories around it. Light, which has no mass, is also affected because it must travel through the same curved geometry. This idea explains phenomena that Newton's law could not, such as tiny shifts in Mercury's orbit and the bending of starlight passing near the sun. Einstein's view of gravity leads to some of the most dramatic predictions in physics. Yet these predictions themselves remain quiet in their everyday workings. When a massive star collapses, it can form a black hole, a region where space-time is curved so extremely that not even light can escape. The presence of a black hole is not announced by glowing surfaces or bright colors. Instead, its influence shows up in how nearby stars orbit and how light is deflected. In a sense, a black hole is gravity taken to an extreme, a pure expression of space-time curvature with almost nothing else to see. It is a silent giant, revealed mostly by its effect on the motion of other objects. On larger scales, gravity shapes entire galaxies and clusters. The stars in a galaxy are not randomly sprinkled throughout space. They gather into spirals, bars, and bulges under mutual gravitational attraction. Gas clouds collapse under their own weight to form new stars, while older stars drift in the combined gravitational field of all their neighbors. In galaxy clusters, gravity binds dozens or hundreds of galaxies together, causing them to orbit a common center of mass. The space between galaxies in such a cluster is not empty. It contains hot gas and dark matter, all responding to the same gravitational pull. Over billions of years, small gravitational imbalances amplify. Slightly denser regions attract more material, becoming denser still until they form the large-scale structures we see in the universe today. Gravity's influence is not limited to grand cosmic scales. Even on the scale of a solar system, it orchestrates a complex dance. The planets orbit the sun. Moons orbit planets. Asteroids, comets, and dust grains all feel the combined pull of these bodies. Resonances occur when orbital periods line up in simple ratios, creating stable or unstable configurations. A tiny gravitational nudge at the right time can move a small object into a new orbit, send a comet inward toward the sun, or carve gaps in asteroid belts and rings. The rings of Saturn, for example, owe their structure to a delicate balance of gravity between the planet, its many moons, and the countless fragments of ice and rock that compose the rings themselves. Even the concept of weight is tied to gravity. On Earth's surface, you feel your body pressed against the ground because Earth's mass curves space-time, and your body tries to follow a straight path within that curved geometry. The ground prevents you from doing so, and what you feel as weight is the result of this interaction. In free fall, such as in orbit, objects feel weightless not because gravity has disappeared, but because they are moving along natural paths in curved space-time without being stopped by a surface. Astronauts in orbit are constantly falling around Earth, their motion determined by gravity at every moment. Yet they experience a sensation of floating. On yet grander scales, gravity influences the overall shape and fate of the universe. The expansion of the universe after the Big Bang is not uniform and unconstrained. The distribution of matter and energy and the attractive nature of gravity determine how expansion slows or accelerates over time. In a universe filled only with ordinary matter and radiation, gravity would gradually slow the expansion, possibly even reversing it in the far future. However, observations suggest a more complex picture, involving additional unseen components like dark matter and dark energy. Still, gravity remains the framework that ties these elements together and guides cosmologists as they study the universe's evolution. Despite its ubiquity and power, gravity is remarkably gentle on the level of individual particles. Compared with forces that operate inside atoms, gravity is extraordinarily weak. Two magnets can easily lift a paperclip away from Earth's surface, temporarily winning against the gravitational pull of an entire planet. Yet, on large scales, gravity dominates because it is always attractive and because mass accumulates. Positive and negative electric charges can cancel out, but masses always add. As galaxies form, the combined gravity of countless stars and gas clouds becomes overwhelming, while other forces largely cancel on large scales. This is why gravity is the primary architect of cosmic structure. In the world of physics, there is still an ongoing effort to reconcile gravity with the quantum description of the other fundamental forces. The theory of general relativity describes gravity beautifully on large scales, while quantum mechanics governs the behavior of particles and fields on tiny scales. Bringing these two frameworks together into a single consistent theory has proven difficult. Attempts such as quantum gravity, string theory, and loop quantum gravity are still under development. Gravity remains a giant not only in the cosmos, but also as a conceptual challenge, silently pushing scientists to refine their understanding of space, time, and matter. Gravity, then, is the unseen geometric framework in which the universe unfolds. It does not flicker or flare. It does not announce itself with colors or sounds. It simply shapes trajectories, bends light, sculpts galaxies, and guides the motion of every star and planet. The quiet steadiness of gravity makes it easy to ignore in everyday life. Yet its influence reaches from the fall of a stone to the spin of a galaxy cluster. As a cosmic giant, it works without spectacle, but nothing in space is truly untouched by its presence. Dark matter, the invisible scaffold of galaxies. Beyond the familiar pull of gravity from stars, planets, and gas clouds lies a more elusive presence. Astronomers exploring how galaxies move and rotate realized that something was missing from their equations. Stars in the outer regions of galaxies were orbiting faster than they should if only visible matter were present. Instead of slowing down at large distances from the galactic center, as expected from Newtonian dynamics, their speeds remained nearly constant. This unexpected behavior pointed to the existence of additional mass that did not emit or absorb light. This unseen component became known as dark matter, and it appears to act as a vast, invisible scaffold that holds galaxies together. The term dark matter can be misleading because it suggests some mysterious substance with special properties. In many ways, dark matter is conceptually simple. It is matter that has mass and responds to gravity, but it does not interact much with light or other electromagnetic radiation. It neither shines nor reflects in any detectable way, making it invisible to telescopes that rely on light across the spectrum. Its presence must therefore be inferred indirectly through its gravitational effects. When astronomers map the rotation curves of galaxies, study the motions of galaxy clusters, and observe the bending of light around massive objects in a process called gravitational lensing, they consistently find evidence for much more mass than can be accounted for by visible stars and gas alone. One of the earliest lines of evidence for dark matter came from studying how galaxies behave within clusters. Fritz Zwicky, a Swiss astronomer, investigated the Coma cluster of galaxies in the 1930s and found that the visible galaxies were moving so quickly that they should not remain gravitationally bound if only their luminous matter were present. Something else had to provide the additional gravitational pull to keep the cluster intact. He referred to this as dunkel materia, or dark matter. At the time, his ideas were not fully embraced, but later observations of galaxy rotations and more precise measurements of mass distributions confirmed that he was pointing at a real phenomenon. Dark matter does not form stars, planets, or glowing clouds, yet it appears to shape the overall structure of galaxies. Simulations of cosmic evolution, beginning shortly after the Big Bang, show that small variations in the density of dark matter grow over time under gravitational attraction. These tiny overdensities attract more dark matter, forming clumps and filaments. Visible matter, made of ordinary atoms, falls into these pre-existing dark matter wells. As gas accumulates and cools, it can form stars and galaxies at the centers of dark matter halos. In this picture, dark matter acts as a kind of framework on which the visible parts of galaxies are built. The luminous spiral disks we see are only the bright tips of a much larger, unseen iceberg of mass. The evidence for dark matter accumulates from multiple directions. Gravitational lensing, predicted by general relativity, offers a powerful tool. When light from a distant galaxy passes near a massive object, its path bends, creating distorted or multiple images. By analyzing these distortions, astronomers can reconstruct the mass distribution of the intervening object. In many cases, the lensing signal reveals far more mass than can be accounted for by visible matter. Entire clusters of galaxies appear to be wrapped in large halos of dark matter, with the luminous galaxies tracing only part of the overall mass distribution. In some systems, such as the Bullet cluster, the separation between ordinary matter and dark matter during a collision of galaxy clusters provides especially striking evidence. The Bullet cluster consists of two galaxy clusters that have passed through each other. During the collision, the hot gas in the clusters, which is made of ordinary matter, interacted and slowed down, while the galaxies, being mostly empty space, passed through with relatively little interaction. Gravitational lensing measurements reveal that most of the mass is not centered on the slowed gas, but instead aligned with the galaxies, suggesting that the dominant mass component did not interact strongly during the collision. This behavior matches the idea of dark matter, something massive and gravitationally influential, but largely non-interacting except through gravity. Despite its importance, the true nature of dark matter remains one of the major open questions in physics. Several candidates have been proposed. Some theories suggest that dark matter consists of new kinds of elementary particles that rarely interact with ordinary matter, such as weakly interacting massive particles, often abbreviated as WIMPs. Other possibilities include axions, hypothetical particles with extremely low mass, or sterile neutrinos, which would be a new type of neutrino that interacts even less than the known types. Experiments around the world are attempting to detect these particles directly or indirectly, using underground detectors, particle accelerators, and astronomical observations. So far, no definitive detection has been made, keeping the identity of dark matter unresolved. Another approach questions whether a new type of matter is needed at all. Some scientists propose that our understanding of gravity might need modification on large scales. Modified Newtonian dynamics and related theories try to explain galactic rotation curves by changing the laws of motion or gravity at very low accelerations. While these models can sometimes reproduce specific observations, they face challenges in matching the full range of evidence, especially on the scale of clusters and the cosmic microwave background. The dark matter hypothesis, for all its mystery, provides a relatively simple and unified explanation for a wide array of phenomena when combined with standard gravity. In the context of the universe as a whole, dark matter plays a crucial role in the large-scale structure. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, show tiny temperature variations that reflect density fluctuations in the early universe. The patterns of these fluctuations, combined with models of cosmic evolution, indicate that there must be a substantial amount of matter that does not interact with radiation the way ordinary atoms do. The best-fitting models suggest that dark matter makes up about a quarter of the total energy content of the universe, while ordinary matter forms only a small fraction. The rest is attributed to another unseen component, dark energy, which influences the expansion of the universe. In simulations that incorporate dark matter, a cosmic web emerges. Long filaments of dark matter connect dense nodes where galaxy clusters form, while vast voids appear in between. When astronomers map the distribution of galaxies, they find a similar web-like pattern. This correspondence between simulations and observations strengthens the view that dark matter is the underlying scaffold on which visible structures are built. In this grand architecture, dark matter is the invisible framework, and galaxies are like lanterns hanging along its strands. Yet for all its cosmic importance, dark matter remains silent. It does not glow, burn, or sparkle. Telescopes do not capture images of dark matter directly. Its presence is deduced from how it bends light and governs motion. The quiet nature of dark matter contrasts with its large-scale impact. Without it, galaxies might fly apart, clusters would not hold together, and the patterns we see in the universe would be fundamentally different. In this sense, dark matter is a giant that never shows its face, influencing the universe through gravity while remaining hidden from direct view. The ongoing search for dark matter is a collaboration between astrophysics, cosmology, and particle physics. Underground detectors are designed to catch rare interactions between dark matter particles and ordinary atoms should they occur. Particle accelerators, such as the Large Hadron Collider, explore high energies where new particles might be produced. Astronomical surveys map the distribution of galaxies and measure lensing effects with increasing precision. Each of these efforts adds a piece to the puzzle. Whether dark matter turns out to be a new kind of particle, a sign of modified gravity, or something else entirely, it represents one of the key unseen forces shaping space. As our instruments and models improve, the picture of dark matter's role in the cosmos becomes more detailed, even if its essence remains unknown. It quietly binds galaxies, anchors clusters, and shapes the cosmic web, all while refusing to appear in our images. Among the quiet giants of space, dark matter is perhaps the most elusive, a hidden scaffold without which the visible universe would look entirely different. Dark energy, the subtle driver of cosmic expansion. If dark matter provides the unseen mass that holds structures together, dark energy appears as an unseen influence that pushes the universe apart. In the late 20th century, astronomers studying distant supernovae made a surprising discovery. They expected to find that the expansion of the universe was slowing down over time, pulled back by the combined gravity of all matter. Instead, the data suggested that the expansion is accelerating. Galaxies far from us are not only receding, they are doing so more rapidly as time passes. To account for this accelerated expansion, scientists invoked a new component of the cosmos: dark energy. Unlike dark matter, which behaves like a substance with mass that clumps under gravity, dark energy seems to be more evenly spread throughout space. It does not cluster significantly in galaxies or filaments. Instead, it appears to permeate all of space, exerting a kind of negative pressure that drives expansion. One way to model dark energy is as a cosmological constant, a term that Einstein originally introduced into his equations of general relativity. He initially used it to construct a static universe, one that neither expands nor contracts. When observations showed that the universe is expanding, he abandoned this idea and reportedly called it a mistake. Yet, the discovery of accelerated expansion has revived the cosmological constant as a convenient description of dark energy. The cosmological constant can be thought of as an energy density inherent to empty space. Even in a region devoid of matter and radiation, space itself would have an associated energy. This energy does not thin out as the universe expands, unlike matter, which becomes more diluted as space stretches. As a result, the relative importance of dark energy grows over time. In the early universe, radiation and matter dominated the dynamics of expansion. As they diluted, dark energy became increasingly significant. Today, observations of the cosmic microwave background, large-scale structure, and supernovae indicate that dark energy accounts for roughly 2/3 of the total energy content of the universe. The effect of dark energy is subtle on local scales. Within galaxies and clusters, gravity from matter is strong compared to the influence of dark energy. Stars orbit their galactic centers, planets orbit stars, and clusters hold their member galaxies in place. Over these distances, the pull of gravity dominates. It is only on the largest scales, between widely separated galaxy clusters, that dark energy's influence becomes apparent. The space between these structures is stretching faster and faster, increasing the distances between them as time goes on. As the universe continues to expand, regions separated by vast distances will eventually move beyond each other's observable horizons, leaving isolated islands of matter within an ever-growing cosmic ocean. The physical nature of dark energy remains unknown. The cosmological constant is a simple mathematical representation, but it does not explain the underlying cause of this energy density. Some theories suggest that dark energy could be related to vacuum energy in quantum field theory, where fluctuations of fields in supposedly empty space contribute a background energy. However, straightforward calculations of vacuum energy predict a value enormously larger than what is observed, by many orders of magnitude. This discrepancy is one of the biggest puzzles in theoretical physics. It suggests that either our understanding of vacuum energy is incomplete, or that some process cancels out most of this energy, leaving only a tiny residue that manifests as dark energy. Other models propose that dark energy is not constant, but changes over time. In such scenarios, dark energy might arise from a dynamic field that slowly evolves, sometimes referred to as quintessence. As this field changes, the effective energy density associated with it could vary, potentially affecting the rate of cosmic expansion differently in the past and future. Observational programs that measure the expansion history of the universe at different epochs aim to distinguish between a true cosmological constant and more complex dark energy models. So far, the data are consistent with a constant dark energy, but uncertainties leave room for alternative possibilities. From the perspective of general relativity, dark energy influences the curvature of space-time on vast scales. In a universe dominated by matter alone, gravity would act like a brake on expansion. The rate of expansion would decrease over time, and depending on the total amount of matter, the universe might even recollapse. When dark energy is included, particularly in the form of a cosmological constant, the equations predicted different behavior. Once dark energy dominates, the expansion begins to accelerate. Galaxies not bound by local gravitational structures recede from each other ever more quickly. This accelerated expansion does not require any pushing force in a mechanical sense. It is a consequence of the way energy and pressure shape space-time in Einstein's framework. One of the quiet but profound implications of dark energy concerns the ultimate fate of the universe. In an accelerating universe, governed by a cosmological constant, structures that are not gravitationally bound will drift ever farther apart. In the distant future, observers within a given galaxy or local group of galaxies might see fewer and fewer external galaxies as they move beyond observational reach. The cosmic microwave background radiation will stretch to longer wavelengths, becoming undetectable. The universe will not end in a violent collapse, but will gradually become dark and dilute, with isolated islands of matter in an expanding void. This long-term outlook is sometimes described as a heat death or big freeze, where energy becomes too evenly spread to sustain significant activity. Other speculative scenarios arise if dark energy behaves differently over time. If its strength increases with expansion, it could reach a point where it overcomes all forms of binding, tearing apart galaxies, stars, and even atoms in a hypothetical Big Rip. Alternatively, if dark energy decays or changes sign, it might allow expansion to slow or reverse, leading to a different cosmic destiny. These adventurous possibilities depend sensitively on the detailed properties of dark energy, which remain unknown. For now, the best supported picture is one of an increasingly dark and isolated universe, driven by a relatively constant dark energy background. Despite its enormous influence on the cosmic scale, dark energy has no obvious direct impact on everyday life. It does not affect the orbits of planets in any measurable way, nor does it influence local experiments in laboratories. Its effects are only visible when we look outward across vast distances and long timescales. Supernova surveys, galaxy redshift measurements, and maps of cosmic structures are the tools that reveal its presence. It is, in that sense, a background influence, shaping the overall story of the universe while remaining imperceptible in local details. Among the unseen forces of space, dark energy is perhaps the most abstract. It does not behave like a traditional force, nor does it clump like matter. It enters equations as a smooth component of energy density that alters the geometry of space-time. It does not swirl, cluster, or form objects. It simply pervades space, steadily guiding the universe along an accelerating path. Its quietness is deceptive, because its effect accumulates over cosmic time, gradually altering the large-scale structure and future horizon of the universe. As observations grow more precise, cosmologists aim to map the expansion history in greater detail, using new generations of telescopes and surveys. By comparing the distances and redshifts of galaxies and supernovae, and by studying subtle patterns in the cosmic microwave background, they hope to constrain the behavior of dark energy more tightly. Whether it proves to be a cosmological constant, a dynamic field, or a sign of deeper changes in our understanding of gravity, dark energy will remain a central piece of the cosmic story. A quiet driver of expansion that cannot be directly seen, but that shapes the universe from one end of time to the other.